Alright, continuing an AP Stat here on Chapter 6. We're still in Unit 1, just going over some practice problems, still manipulating some ideas of finding mean, multiplying or adding or subtracting to means and medians, as well as mins and maxes, but then also what happens to them with standard deviations, variances, interquartile ranges, things like that, and then also finding some z-scores. Again, if I'm moving too quick for you, please pause the video, write everything down so you can kind of soak it in that way before we move on. But some more practice problems here. A friend tells you about a recent study dealing with a number of years of teaching experience among current college professors. He remembers the mean, but can't recall whether the standard deviation was 6 months, 6 years, or 16 years. Tell him which one it must have been and why. So, logically, all right, he can remember the mean, but he can't recall whether the standard deviation was 6 months, 6 years, or 16. So, the standard deviation of the distribution of years of teaching experiences for college professors must be 6 years. Okay? Now, think about it this way. College professors can have between 0 or 40, maybe even 50 years of experience. They could, right? I mean, just logically think about it. You could have if you went right out of school, you're 21, 22, you go right for your master's, which is like another 2 to 3 years. So even if we lowball it to like 24, 25, when you instantly get your first teaching gig out of college and then you teach, you could, I guess, teach into your 70s if you wanted, but more than likely, it's probably more like 40 years. And a workable standard deviation would cover most of that range, right? So that means plus or minus 3 standard deviations, which is a total of 6. So if you're guessing that they probably taught in between 40 or 50 years, what they're implying is if you take that 40 and divide it by 6, or you take that 50 and divide it by 6, it's in between 6 to 8 years would probably be a better standard deviation. Not 6 months, that's only half of a year. On top of that, 16. So we went with the max. We went with the worst case scenario would be if they taught for 40 to 50 years. That's why we were going with that. So that's why our bet is probably that the 6 years is the right option, guessing. A popular band on tour played a series of concerts in large venues. They always drew a large crowd, averaging about 21,359 fans. While the band did not announce, the standard deviation, which of these values do you think is most likely to be correct? So again, you got your average amount of fans right there. Okay? So if they're looking to see what is probably the better bet of fans, even if we went with, if they average those amount of fans, even if we went with something insane like 100,000 fans came, right? Like that's the most that could possibly come out. And to get that within 6 standard deviations, we're looking at around 16,666, meaning they're averaging this, and I went with an exorbitant amount, 100,000 fans. That isn't even this number, okay? It's not even that high yet, so that's too high. This obviously seems too low. How could they even possibly get an average to be that way, right? Because think about it this way. If I take those numbers, each of them, and I multiply it by 6, which is most of the data falls between those standard deviations, is basically what I'm saying. That would mean that if I multiply this by 6, or this by 6, or this by 6, trying to figure it out, again, the standard deviation is probably more than likely 2,000, because of 200 fans seems much too consistent of it. Like, you're telling me that all the time we're within 200 fans. I mean, that's a small group, and that's very consistent is basically what it's saying. All right, even smaller would be 20. It seems like a rock concert attendance could vary pretty drastically, but if a standard deviation of 200 fans is too small, then so is 20. So 20,000 is too large, because what's the likelihood that one show has you average 21,000, but now you have even more, like just randomly 20,000, like plus or minus. We could go between anywhere between no fans show up to 40,000 fans. I mean, the likelihood, that doesn't seem very likely to me, which is why this is probably the better bet as well. The Environmental Protection Agency fuel economy estimates for automobile models tested recently predicted a mean of 24.8 and a standard deviation of 6.2. Assume a normal model. We now know that it is normal. So they want us to draw the normal model and clearly label it. So point is, that's the middle. I would go up one standard deviation, then another, and then another. I would also go down a standard deviation, another, and label them with the 68-95 rule, which is what this is. So I added 6.2, 6.2, 6.2, subtracted 6.2, 6.2, 6.2 to get what my model is. Then it says, in what interval would you expect the central 68% of autos to be found? So you're supposed to look at that and be able to decipher. If you're looking at that, you got the normal model, all right? Approximately 68% of the cars are between the 18.6 and 31. That's where 68% of them are. About what percentage of autos should go more than 31? Well, more than 31 is whatever this section is plus this section plus this section. So, or you could take the 68 and take that little portion. So you're just subtracting is the point. So about 16% of the cars, because basically I believe this is 13.5 and this is like 2.35, and then this would be even less. So the point is, as you add them up, it's approximately 16% would be there to the other side, because you can break all of these up into little portions. And then it says about what percent of cars should get between 31 and 37.2, and that's the 13.5% that I was talking about. And then describe the gas mileage of the worst 2.5% of all cars. And then it says the worst 2.5% of all cars are expected to have fuel economy of 12.4 or lower. 2.5 low. Describe the gas mileage of the worst 2.5, which would be what's left over here. That's roughly 2.35, and then that's roughly 0.15. So everything from there down. So fuel mileage of 12.4 miles per gallon or worse. So IQ tests are standardized to a normal with a mean of 100 and standard deviation of 16. And then again, that wants us to draw our model. So we have our mean, and we would go up 16, and we would go down 16 the whole way, and then label it, which is what we did. So up 16, and we went down 16, and then 68, 95, 99.7. In what interval would you expect 95% of the data? 68 to 132, right? As you're looking at it, 68 to 132. Then it says about what percent of people should have IQs of above 116. Well, that's about the 16% that we said. That's the 2.35. That's the 0.15. That's the 13.5. So about 16%. Between 68 and 84 is also about 13.5%. And about what percent of people should have IQ scores above 132? That is the 2.5% that we were talking about. If it's 95% in here, then it's 2.5 and 2.5 on either side. In example 17, we suggested that the steers were normal, right? With this, that means the mean, and that means the standard deviation. All right. What weight would you consider to be unusually low for such an animal? So anything unusual would technically be over 2 standard deviations above or below. So if we subtract 84 twice, basically anything below 984 would be starting to get unusual. And 1152 plus 84, anything above 1320 would start to be. So that's what we're basically saying here. 2 standard deviations above or below the mean is where that would happen. We would expect to see steers below around this. So now very rare is what it's saying. If we get even more rare, and ironically enough we're talking about meat, but if we get even more rare, would be 3 standard deviations above. So anything that's below 900, that would be really rare. Anything above 1404, that's also extremely rare. All right. You looking at this one again, we're saying that this is normal. We propose the IQs, and when they list it with it being normal with the mean standard deviation, what IQs would you consider to be unusual? Again, same idea. Subtract 16, subtract another 16. Anything below 68 would probably be unusual. and take your 100 plus 16 plus 16. Anything above 132 would also be unusual, is basically what they're saying, right? Above that. And also below, so anything above or below. But again, we would expect to find someone with an IQ of over 3 standard deviations, very rare. So also the other way around, that would also be very rare. If we went below, that would be like in the 40s, I guess 42. Anything 42 and under would also be very, very unusual. A forester measures 27 of the trees in a large woods that is up for sale. He found a mean diameter of 10.4 inches and a standard deviation of 4.7, and supposed that these trees provide an accurate description of the whole forest and that normal model applies. So we know it's normal. I also not only know it's normal, I know the mean and I know the standard deviation. So I can easily draw my picture because I have the mean, and using the empirical rule, my standard deviation 4.7 up and down to find my stuff. So I drew my model and I labeled the 68, 95, and 99.7. It says, what size would you expect the central 95 of the tree to be? Between 1 and 19.8 basically is what we're saying. About what percent of trees should be less than an inch? Less than an inch would be down here, which is, if this is 95, this outsides would be 5, or 2.5% for that one. What percent of the trees should be between 5.7 and 10.4? About 34%, because you'd split that in half. And then what percent of the trees should be over 15 inches? All right, now that's not exactly 15, so we might have to do some fuzzy math in order to figure that out. But technically, we would go from here down, and there's a way to make this more accurate and actually use something with it. But again, over 15, because it could technically be 15.04, and that would be in this side. That would also count towards it. So roughly, for this to be accurate, over 15.1 is what they should be saying. But we could find it using a calculator to make it more exact. We could plug it into the calculator and do like a normal CDF in order to find that. When I come back, we can talk more about the practice problems with rivets.